Good morning, students. Today I am going to discuss with you the topic of superconductivity, right? Superconductors, or superconductivity, or types of superconductors, right? Before that, you had done what are semiconductors, what are insulators. We know that insulators whose conductivity is very low, insulators, right, whose conductivity is zero, we can say, whereas in case of conductors in which the current flows through them, right. And you know about semiconductors whose conductivity lies between insulators and conductors, right. So here I am discussing about superconductors. The superconductors whose resistivity is zero at a specific temperature, we can say, those are called superconductors. And what is superconductivity? So firstly we will introduce the electrical resistivity of many metals and alloys drops suddenly to zero when the specimen is cooled to a sufficiently low temperature, that is temperature in liquid helium range, right. This phenomena is called superconductivity, and it was observed by the physicist Kimberling Ons in year 1911, right. The material whose resistivity drops to zero at a particular temperature, that temperature is called critical temperature, right. Okay, again I will repeat, I'm repeating this thing. Critical temperature, it is denoted by the symbol Tc. The temperature at which the resistance of a material suddenly falls to zero is known as critical temperature, right. Above critical temperature the material is behaving like a normal conductor, right. And before that the material is below critical temperature, the material is behaving like a superconductor, right. Or above, here it's mentioned above critical temperature a material has a particular value of resistance, right. Below, its resistance is zero, right. Above critical temperature material is said to be in normal state, what is behaving like a normal conductor, and below critical temperature it is behaving like a superconductor, as we had we just see in this graph. Here material below critical temperature, suppose this Tc is the critical temperature, this is graph between resistivity versus critical temperature. Here above critical temperature the material is behaving like a normal conductor, right, and below critical temperature the material is behaving like a superconductor, right. So that's why the materials are called superconductors, because whose resistivity is zero, right. Again I repeat the definition of critical temperature. So what is critical temperature? At a particular temperature the resistance of a particular metal becomes zero and conductivity becomes infinite. The temperature at which conductivity becomes infinite is known as critical temperature. This phenomena is called superconductivity. I repeat the same thing. This critical temperature, this critical temperature is different for different superconductors, right? So here it's mentioned in case of mercury. Here it's mentioned here electrical resistivity of pure mercury dropped to zero at around 4.2 degree Kelvin. Means we can say the mercury becomes superconductor at this temperature, right. This new state of mercury is known as superconducting state, and at this temperature conductivity increases infinitely, we can say. So here are various properties of superconductors. First property is zero electrical resistance, we can say. Zero electrical resistance means a superconductor is characterized by zero resistivity. It is not possible to test the resistance here experimentally, right, that the resistance is zero. The testing of resistance was tried by one method in which material was connected in a circuit, right. The potential difference across the ends were measured. Suppose this is a material or superconducting sample. Here at the two ends the voltmeter is connected and it is connected to a battery, right. So here normal current is flowing. Here in this case, here some potential is applied. In this case the potential is zero, right. So it showed further that the material is in normal conducting state. When the material is in normal conducting state, a voltage drop is observed across the ends of a superconductor here, right. So here we can see that there is some voltage, right, which is voltage, means voltmeter is having some finite value, right. When the material is in the superconducting state, when the material is superconducting state, and that is when cooled below its critical temperature, if we cool that material to below its critical temperature, the potential difference across the ends of the material shows sudden drop to zero. Here it's mentioned that the potential difference is zero in case of superconductors, right. So here it's mentioned in this diagram, here temperature is greater than critical temperature, here temperature is less than equal to critical temperature, right. So here some resistance is there, here the resistance tends to zero, E by I tends to zero in case of superconductor. Okay, this name of the scientist who had developed the superconductivity is called his name is Kamerlingh Onnes, right. So it's mentioned here, right. So this is the this is regarding how a material becomes a superconductor. Now next main thing is, next important topic is our Meissner effect. What is Meissner effect? This phenomena states that when a superconductor is cooled below critical temperature, this phenomena states that when a superconductor is cooled below critical temperature and placed in magnetic field, then the flux is excluded from the bulk of the specimen, right, or flux is excluded from the specimen, we can say. This effect is known as Meissner effect. Again I repeat, this is a diagram for that. Here external magnetic flux is applied to the specimen of a superconductor, right, and when it is placed in external magnetic field, here when the temperature when it is cooled below critical temperature, we can say, and then the flux is excluded from the bulk of the specimen, right. The flux can't we can say penetrate through this specimen when it is cooled below critical temperature, here in this case, right. Here the external magnetic field tends to zero in this case inside the specimen, right. So this is the Meissner effect, and it is important as per paper point of view. So in 1933 Meissner had discovered this effect, right. In this case a superconductor completely expels any magnetic lines of force which are initially penetrated through the specimen, right. So again I repeat the same definition, but just make or in between these two. Hence the expulsion of magnetic flux, here you can see the expulsion of magnetic flux during the transition from normal conductor to a superconducting state is known as magnetic flux, is known as Meissner effect, we can say. Okay, again I repeat, when the field is switched off, magnetic field is not trapped by the superconductor as shown in this figure when it is cooled below critical temperature. This is the Meissner effect, this main thing. Again this Meissner effect is reversible. Okay, again this thing, when the temperature is raised from below critical temperature, the flux suddenly starts penetrating, means if the temperature is suddenly increased, the flux suddenly starts penetrating inside the specimen. This is reverse effect, is also reversible, we can say, right. So at here we can see the flux suddenly starts penetrating the specimen at critical temperature. As a result, material returns back to its normal state, we can say. So magnetic induction inside the specimen, that is given by B is equal to mu naught H plus M. Here H is the external applied field and M is the magnetization produced within the specimen, right. So B is equal to mu naught into H plus M when the material is behaving as a normal conductor, right. And when temperature is reduced below critical temperature, then B becomes zero, means magnetic field inside the specimen is zero. So if this is the Meissner effect, put this value of B here in above equation. After putting this value, you will get this thing, mu naught into H plus M is equal to 0. and take mu naught to this side, it is constant, again 0. H plus m is equal to 0. M is equal to minus h, but susceptibility of the material is defined as m by h. If m is equal to minus h, put the value of m minus h here. Xi becomes minus 1, means Xi minus 1 is the property of perfectly diamagnetic materials, means superconducting state is characterized by perfect diamagnetism, right? So this is the question, sometimes it appears in exams: prove that superconducting state is characterized by perfect diamagnetism, or superconductors also behave as a perfect diamagnetic material. Then you have to prove this derivation in this case, right? Now next is, what is the origin of Meissner effect? Origin of Meissner effect: here we can see, when we apply external magnetic field to a specimen of a superconductor, the electric current is induced inside the body of the superconductor, right? The magnetic field produced by this induced current exactly cancels the applied field, therefore net magnetic field inside the superconductor becomes 0. So this is the origin of Meissner effect. The superconductor is a strong diamagnet, but at the same time it should be noted that superconductivity is not only strong diamagnetism but a new type of strong diamagnetism, right? So before that we had done critical temperature. Here another definition is critical magnetic field. What is critical magnetic field? The minimum applied magnetic field necessary to destroy the superconductivity and further restore the normal resistivity is called critical magnetic field, or Hc. Here Hc depends upon temperature, we can say. This is the graph between critical magnetic field and T by Tc. Here you can see that this is the curve. This is the critical magnetic field as a function of temperature. Here below critical temperature, the material is behaving like a superconductor. So curve is a parabolic and it can be well represented by the relation this. Here critical magnetic field is equal to H naught into 1 minus T by Tc whole square, bracket close, where H naught is the critical field at absolute 0, right? And typical value of H naught is 5000 ampere per meter per A by M, we can say. So there are some examples related to it, which I had sent you in a PDF. You can go through the numericals. Okay, our next topic is types of superconductors. This we will continue in the next lecture. Thank you very much.